We are Team Savvy Stent, a group of 5 Rice bioengineers, and we are developing an implantable medical device to monitor abdominal aortic aneurysm in real time. So before we talk about our solution, what is the problem that we're solving? So what is abdominal aortic aneurysm? The abdominal aorta is the primary artery that transfers blood flow from the heart to the abdominal and pelvic organs and tissue. Abdominal aortic aneurysm is a disease characterized by the gradual swelling and eventual rupture of the abdominal aorta, which has a 90% mortality rate. Once diagnosed, a patient undergoes endovascular aortic repair, in which a stent graft is inserted to strengthen the walls of the aneurysm and block continuous fluid flow. However, a third of this treatment fails to stop aneurysm swelling. So what is the current solution to make sure that the stent is working and no major leak is developing? CT scans administered monthly to yearly. Unfortunately, CT scans have a number of drawbacks. Number one, the average cost per abdominal CT scan for a patient living in Houston, Texas is approximately $3,200. Number two, patients are exposed to serious radiation harm, which increases the likelihood of cancer. Number three, and because patients have to go to the hospital, compliance for attending their CT scans decreased to 50% after 5 years. This is a major problem.
Our team believes that the leaking of the blood around the stent grafts can be detected another way. As it turns out, blood has a drastically lower impedance than muscle. Therefore, the leaking of these stent grafts can lead to detectable change in the bioimpedance of the surrounding tissue. Using this knowledge and with support from our sponsor company Serranis, our team has developed the Savvy Stent solution, a one-time implantable medical device that can monitor the changing physiology of the abdominal aorta in real time. In designing our prototype, we aim to hit 4 criteria. The first is accuracy, as our prototype has to be as accurate as a CT scan, which is the current gold standard. Second is sensitivity, as its resolution must be as sensitive as a regular CT scan. Third is intuitiveness, as patients and doctors must be able to easily understand patient information generated by our medical device. And fourth is cost, as it should be cost significantly less than the CT scan.
Our device is a modified catheter with 2 transmitting and 2 detecting electrodes. After creating an electric field with the 2 transmitting electrodes, the 2 detecting electrodes will monitor any changes within the field. The underlying hardware and software that enables this detection are proprietary technology from our sponsor company. Our device is designed to be implanted in the ascus veins, centimeters from the abdominal aorta. The ascus vein is an auxiliary branch off of the inferior vena cava, wrapping around the abdominal aorta. This strategic placement gives us unprecedented access to the abdominal aorta and to detect leaks with minimal invasion. So far, our team has performed several computational models to identify ideal electrode distance and configurations. We've used Simplifier software, which simulates the electrode impedance detection of 70 cc's of blood rupture. From this study, we have identified the maximum distance the electrodes could be placed from the abdominal aorta. Next, we developed a benchtop model that mimics muscle, artery, and blood in order to test implantation distances and rupture sensitivity of our device.
To demonstrate, placing the catheter in saline that mimics the impedance of blood will cause the impedance reading to drop. This will subsequently cause an LED to light up and notify patients and doctors.
Finally, we have performed 2 sheep studies, which resulted in the successful detection of aortic ruptures. As you can see, the impedance of the aorta before rupture was around 80 ohms, and after was 50 ohms. That's a 40% decrease.
AAA is a dangerous disease and close monitoring is critical. However, CT scan, the current gold standard for monitoring, has a number of drawbacks, namely cost, radiation, and inconvenience. We developed an implantable device to monitor abdominal aortic aneurysms real time, a system that is affordable, inflicts no radiation, and provides at-home convenience. Further, our device is accurate, sensitive as CT scans, and intuitive. In addition to computational and benchtop work, we have conducted 2 successful large animal studies with Texas Heart Institute to validate the effectiveness of our prototype. Future studies will focus on developing a more personalized electrode implantation system and optimizing our thresholds for accuracy and sensitivity. We presented at the Rice Engineering Design Showcase and the Bay Area Rice Bioengineering Showcase, where we won the Most Investable Award, and we are scheduled to present at the FDA BMES Frontiers in Medical Device Conference this summer. We thank Rice University and the sponsor company Serranis for this great opportunity.